Okay, so welcome to this. So this is, I think this is the last RMG focused lecture. So originally this is, I think on the schedule this is called pruning, but I decided that there was some stuff that what was going on in the Run RMG lecture was a bit big to begin with, so I moved some of it to this lecture, which is more on some of how to run RMG when there's sort of there's a number of sorts of problems you can run into running RMG, and these are sort of ways to mitigate those issues and avoid them. So first, I'm going to talk just a little bit about about speed with RMG. And then speed and memory, and then I'm going to talk about pruning for a bit, and then pathway pickup problems. So in general, RMG has two scaling regimes. It has, so when your model is very small or when your molecules are very large, you're limited by how fast you can react to species. And this is because we're primarily limited by doing all these isomorphism comparisons that are involved in the process of generating reactions within RMG. However, as the run continues, and especially when you have smaller structures that are less reactive sites, less resonant structures, you start to become limited by how fast you can simulate the system. I think for propane, this maybe takes place around 500 species. So which for people making some models, that may be quite large. For people making other models, that actually may be quite small. And the transition is very system dependent, and so you kind of have to figure it out based on what you're running. There are a lot of tricks for getting the simulations down, but we don't have nearly as many tricks to get the react time down, although we're working on parallelizing these processes. I think Agnes is doing a lot of work on that. So as far as memory, species and reactions are sort of the things that you can think about as taking up the most space when you're running a given RMG run. And what you can also think about is you can generally neglect all of the stuff in the core because the edge is so much larger than the core in the RMG model. And so another thing to think about is that, well, so you have your core and then you have your edge built around it. And so the edge sort of forms some sort of kind of reactive surface to the core. And when you think about it that way, naturally it kind of comes that you can see that the edge scales with the core. However, how many connections you have leaving the core that connect with the edge can depend on your system. For some stuff, I think for liquid oxidations, we've seen drastically different scaling than with other standard models, like say small combustion models. So what was an early problem with RMG is that the memory consumption would just get too high because the edge got large. And that basically prevented them from building a lot of these large models because they just run until the processor ran out of memory, and then the job would have to stop. And so Kei Hong, a former student here, put a lot of effort in, and I think also Connie Gao did some work on this, some ways to reduce the memory consumption by reducing the size of the edge. So here's a plot of memory consumption by the number of species in. Oh, sorry.
What's the big O scaling with respect to the number of species in the edge?
For
is it like linear in memory, or is it super linear?
In memory?
Yeah.
This is the.
Yeah. There we go. Thanks.
This is the exact plot for natural gas oxidation. Although it may be different for different models. So this is just sort of some general way to look at it. This is. So this is number of species, so you're also increasing the number of reactions when you increase the number of species, as this mechanism is so the idea behind pruning is essentially that we look at the model, and when the model gets large, we remove some species and reactions from the edge, ones that we think probably aren't important, and essentially that they go away and they aren't looked at anymore when RMG runs. And so the original method that they developed to do this was Flux-based. A year two ago, I built a method that works on Gibbs energy of formation that has it fixes some of the issues that you can sometimes run into with the Flux one, but the Fluxes in general is more robust, is a better way to do this. But the energy-based one, it does work. So to talk about Flux pruning, so first we're going to go and look back at the RMG algorithm and how that kind of works. So we've got some core edge systems, some species in a core, we've got some edge species, we simulate, and we find this species D here, and while we're simulating, what we note is that D exceeds the tolerance moved to core, and so we select D, and we move D into the model. So what we can also look at is, so we have this tolerance moved to core, but with pruning, we also have this tolerance interrupt simulation. And the tolerance interrupt simulation is if some rate ratio, this ratio between the edge species flux and the characteristic flux, gets higher than the interrupt tolerance, then the simulation terminates. However, in pruning, something that they thought was very important is that you complete the whole simulation before you decide whether reactions are important or not. That you made it all the way through so that before you tell whether reaction X is an important reaction or something you can just totally toss. And so, and what they also said is that tolerance keep an edge. And so what happens is if the simulation completes, you do pruning, which something that's also important to know is that pruning takes part in 2 steps, which is something that is a really common misconception with people about pruning. So the first step is that the algorithm goes through and it finds all of the species that are entirely below the tolerance keep an edge for the entire simulation. And if that's true, it just removes it from the model. However, oftentimes that's not sufficient to get you down to the maximum edge size you specified in the input file, which actually isn't, the maximum number of edge species actually isn't maintained strictly by the Flux algorithm, which is another important thing to know. So what happens when you complete the simulation, if you complete the simulation, it does that, and then it goes through and ranks all of these species based on their rate ratios, and removes the species with the smallest rate ratios until the number of edge species is the same as the maximum edge species. However, it's important to remember that this only happens if the tolerance interrupt isn't interrupted, if the model isn't interrupted while it's simulating. So in this sort of situation, where we have the species that goes above the interrupt tolerance, when we simulate here, RMG gets to here and it stops. And since it didn't complete the simulation, it doesn't do any flux pruning, and the edge, and when it finishes, the edge size may be larger than the maximum number of edge species.
Could you go through the interrupt, the logic behind the interrupt?
Sure. So you mean in terms of why we have it?
Yeah.
So originally, I believe the original RMG didn't have it at all because they just kind of went through and they'd simulate until they hit something that violates the move to core tolerance, then they'd stop the simulation, they'd start over. But the tolerance interrupt is essentially an argument that you can set it to basically say if something violates the interrupt tolerance, then the flux is so large to that species that you don't trust that RMG is representing the system accurately anymore. In general, the real truth of the matter is that, especially in early simulations, RMG is almost never representing the reactive system properly. But it's sort of so. But this is sort of a more extreme case, and so essentially, if you set the tolerance interrupt lower, what you're saying is that you don't trust RMG to pick species after some species reaches this flux that's so large. I use it a lot for when I'm taking multiple species at a time. That's another important parameter for that. But for flux pruning, as I'm going to talk about in a minute, in general, a lot of times they actually set this to something just so arbitrarily large that it always completes the simulation, which is one approach to dealing with this.
So when
when you say it completes the simulation, do you mean one iteration of the simulation?
Yeah, it just runs one simulation, decides what species to add, and then it starts over.
Okay.
Oh, yeah.
So what actually happens when you get the interrupt? Do you add that species to the core and start over, or do you backtrack?
Oh, when it interrupts, it just adds the species to the core, and it continues. So if you don't, suppose you're doing a regular RMG run, you're not doing any pruning. If you're not doing any pruning, it doesn't really matter, and you're not adding more than one species. It doesn't really matter whether this can just be the same as your tolerance move to core, because otherwise you simulate, you add your one species, and then you just simulate the whole rest of the thing, and then you stop and you add that species. So if these are the same, it just reaches this, finds the species, adds the species, ends the simulation, ends it to your model. Does that make sense?
Yep.
Okay. So the recommended, let's skip that. Yeah, I know it talks about that. So the recommended parameters in general are that the tolerance keep an edge should be around 1/10 of the tolerance move to core. And so the tolerance interrupt simulation, it needs to be high enough that you complete the simulations regularly, because otherwise, if it doesn't complete regularly, you don't get any actual flux pruning, which is one thing that when I talk about thermodynamic pruning, that thermodynamic pruning kind of solves. If you desire all of them to complete, usually 1E8 is usually sufficient to do that, although I think Max found some cases where that isn't sufficient, and so we use thermo pruning for that. But just to clarify, so this, typically, this should be about 1/10 of this value. And this should be reasonably larger than this, and perhaps very large. There's some more guidelines. We're going to get you guys the RMG cookbook that I'm still reviewing and fixing it, going through and adding stuff. But that will have stuff on what to set, guidelines on how to set all these model parameters for all of these different systems I'm talking about right now, which are can get quite complicated and difficult to decide. So here's an example of memory consumption for pruning versus a non-pruning algorithm, where you can see that being able to prune the edge species lets us able to keep the memory consumption about constant, whereas without the pruning it would just go off until it crashes the node. And because you're able to do that, in general, if you're pruning for these large models, if you're pruning, you're able to go out farther, and so you're able to get better models than you are if you're not pruning. Because if you're not pruning, you have to stop when you're out of memory. Okay, so thermodynamic pruning. So in principle, the idea is that we look at species that have really unfavorable thermodynamics, and we remove them from the model. Which in principle makes a lot of sense, but the one trick is defining a scale to decide when something's really big relative to other things, and also relative to temperature and all of these other sort of things related to your simulation. So in this case, I scaled it by the difference between the maximum Gibbs energy and the minimum Gibbs energy of all simulations, and then we shift by the maximum. And then we remove a species if this number is greater than our tolerance to keep species at edge, which essentially, because of how we've set Gmax, what this means is essentially how much bigger is this than the maximum, as scaled by the difference between the maximum and the minimum. And what's nice about this one is that unlike flux pruning, the generated species are actually entirely prevented from entering the edge. They never enter the edge, they never take up memory, and we're always able to, because every time after we add species, we just go back through, dig through the edge, and remove the species with the largest thermo, and with the least favorable thermo until we reach maximum edge species. And we also, there's also, so we have the tolerance, and then we have the maintaining maximum edge species, just like we do with flux pruning. So setting parameters, this is a little bit simpler than flux pruning. Usually, ThermokeepSpeciesinEdge, usually between 0.1 and 1.0. You might want to set it a bit higher if you didn't see the job, because the scaling, because this depends on, especially at the beginning of the model time, it depends on what your maximum Gibbs energy species and what your minimum Gibbs energy species is.
How do you keep this from just simply tossing out large molecules? Am I missing?
You mean,
So you're talking about a Gibbs energy of formation. So if I have a molecule that's twice as large.
so usually, typically the reason you have that large molecule is because you started with it.
Okay.
And so if you started with it, that scale will generally, especially if you seeded it properly, you usually have something that's has a really small thermo and something that has a really large thermo.
Okay.
And so it should, when you scale it that way, it usually works out.
Okay. So I guess this is for the assumption of pyrolysis, where you're always breaking things apart, as opposed to if you're polymerizing something which you.
There may be a serious problem if you tried to do polymerization with this. I think some people are starting to work on that, but we haven't done much with polymerization. But that may be problematic in this case. So let's take a break and run the minimal thermal filter example in the examples file. I think it's still at the tiny URL, right? Is that still open, or?
It should still be open.
Okay. Do you know what it is?
I thought you did. RMG examples.
Okay. So HTTP and
tinyurl.com.
okay. In RMG. So in this case, for this example, we've kind of done sort of typical RMG parameters, but we've set the min core size for prune to 2, which is a really, really bad value to set it to, but it's good for demonstrating in a quick example. Because otherwise, the reality is that all of the good pruning examples take take several hours to run. So in this case, this example is just sort of meant to demonstrate, to run it and demonstrate the technology. So we've set that really small. Usually you'd set this to about 50 or larger. And then we've set the tolerance to about 1.0. Are we good? Okay. So to kind of look at this, so there's a few things to note. So we've set the maximum edge species to 100. So one thing we're kind of thinking about, and we're kind of hoping to happen, is that we're keeping our number of edge species around 100. Which we actually aren't quite doing if you notice here, because in this case we have about 319 reactions, and this is because there's another restriction within the pruning algorithm, and that's that you can't remove a species unless it's been in the edge for 2 iterations, which is in general, which is actually quite important. I've used it in a few cases. I've tried to adjust it on a few occasions, and you can get some pretty bad results if you do that. But what we do see here is once we get through those iterations and we're here, it starts being able to remove species, starting with the ones that are the least stable, like this one. And then once more stuff becomes eligible, it starts to pick off a lot of these bi-rats and tri-rats here. Any questions on thermodynamic pruning and pruning in general? So we'll do a little comparison here of the 2 pruning methods. So Flux pruning requires a simulation to do any of the analysis. It does. Well, thermodynamic pruning doesn't require that. The one really nice thing that's valuable about the Flux pruning is that it's much more directly related to how you would add a species into RMG than the thermodynamic pruning is. So using Flux pruning, you're much less likely to toss something out that RMG would have added. The sort of general assumption in Flux pruning is that species that aren't important in the model at that moment won't be important later. And the thermodynamic assumption is a bit more thermodynamic in that it assumes that if you have a high Gibbs energy, it won't be important. Both of those may be accurate to varying degrees, and it's also going to depend on your model type. One nice thing with thermodynamic pruning, which I would argue the only real nice thing is it's much better at maintaining a maximum edge species than flux pruning is, and that's the only the primary advantage of it. Yeah. Thermodynamic pruning also saves you a little bit of time if you have a very large enough model that you're in the simulation regime. And other important notes: a maximum edge species of about 100,000 typically corresponds to about 16 gigabytes of memory. And just to reiterate this again, flux pruning only has an effect when the simulation finishes. So you have to set this interrupt tolerance larger than the move to core tolerance. Okay. Are we good on pruning? Okay. So now we're going to move on to pathway pickup problems. So far, we've told you about this great idea that we can simulate these mechanisms and look at the fluxes, and we can decide what's important in the mechanism. And it's this great, brilliant thing that, oh, we can just go, we can simulate them, we can figure out what's important in all of these things. But it turns out the algorithm, the idea behind the flux, well, it's a lot better than just picking stuff randomly. It has some issues with it that can happen sometimes. And while in general it works pretty well, there are some cases where it has trouble picking up the important chemistry. And so this section is going to talk about a few, two real problems, one theoretical problem, and ways that we have to mitigate them. So a disclaimer on these is that the vast majority, maybe even more, 97.5, maybe even 99% of the time, RMG misses stuff because your chemistry is bad. And your rate estimates are incorrect. Pickup issues incur in spite of this. However, as you can imagine, when they do happen, they're really, really bad. Because when pickup problems happen, improving your parameters won't solve the problem because RMG is not picking it, just not picking it up. Although you can, usually if you can drop the tolerance low enough, it'll pick up this stuff anyway. The problem is when you're dealing with a large model and it's infeasible to drop the tolerance low enough to deal with it. So first I'm going to talk about the orphan radical problem, which is the simplest problem. So suppose you have some species A that can react back and forth with B, and B can react to form C and D. And suppose A is in the model. So A is in the model, it gets some flux to it, it gets some flux going to it, and then it forms B. And so the flux of B is high, we add B. And now what we do is we look at these two rates. And so suppose they're about the same rate. And we simulate the algorithm forward, and it picks one of these species, and let's say it adds C. So now there's an interesting thing happens once we add C. And the interesting thing that happens is that now the flux going through to B has a place to go, instead of when it did before. And since it has a place to go, you have this flux going to C, so the concentration at B doesn't nearly reach peak as high as it would have otherwise. And because of that, once you add C, the flux to D is much, much lower. In fact, so this is the plot of this sort of test example, which is where this blue is the concentration of or the rate of B to D or B to C when they have the same rate. When just A to B is known, we get this really high flux. But once we adding B to C drops the flux down to this level, the flux from B to D. And once we add B to D and we get the real flux is even lower. Let that sink in a little bit. And what this tells us is that RMG is directionally dependent. what stuff's in the model and what stuff isn't in the model changes how RMG perceives stuff to be important. And whether you have nearby species or reactions in the core or edge affects whether species are seen as important enough to enter the core. And this has become the most common example of this problem that we've observed is that B is some radical. And missing the side, because it's missing this side pathway, because the side pathway flux has dropped to this because we have this one, because we're missing the side pathway, we get the concentration of B incorrect. And than it otherwise would be. And this is called the orphan radical problem. And what it does is it causes RMG to add the direct pathways and miss a lot of the side pathways that have a really strong impact on the concentrations of the radical species. Any questions on this? This one's a bit. Honestly, I think this is probably one of the most interesting things I get to talk about. But the one nice thing with this is that we at least have some effects. We have some ways that we can look at this, and I built some tools that help alleviate this problem. However, let's consider a different situation, a thought experiment, which I call the catalyst problem. So suppose we have this core with A and B, D and E is the final product, and A is our reactant. And this is sort of the general pathway. But suppose perhaps there's some edge species C, and perhaps if we'd added C to the core, we'd have found out that there was some edge species Q. Now we don't know that Q exists. We don't even remotely know that Q exists because we've looked at the edge. We at least looked at C and saw that C was there, but we don't know anything outside of that. But suppose it actually turns out that there's some reaction that Q catalyzes, hypothetically, purely hypothetically, between A to E that's much faster than this pathway. So if this was the situation in real life, this would be horrible, because what this implies is that we have to drop our tolerance low enough to resolve Q, because otherwise it's impossible to get this mechanism correct. The good thing is that most of the mechanisms we work with in reality aren't this nasty and don't have this degree of a problem, although you could hypothetically have this problem. And what we get instead is called the chain branching problem, which is, so chain branching is sort of so in this case we have propane, and propane adds these oxygens, does some stuff, and eventually it breaks off an OH, goes through this cycle that makes 3 OHs. And what's really important about this pathway is that is that every time you take one radical and you make 3 radicals, which drastically speeds up the chemistry that's going on for an ignition problem. And these reactions have a really strong influence on ignition delay. However, they can still have that strong influence even if they're really low flux. And this is sort of the more common example of the catalyst problem, which isn't quite as bad because if you think about it enough, what you'll realize is that this can be important at low flux, but it does have to have some flux for this to matter at all. So you do have to have some degree of flux going through this process, but it can be much lower than the rest of the system, especially for large species where you may have there are a lot of different ways for these cycles to happen, and you could have a lot of different pathways that contribute to the overall ignition. And if you're missing a large portion of them, even though each individually isn't that important, you need all of them together to predict the ignition properly. And so this is a bit more the more practical case. So there are sort of 2 ways to combat these problems right now. So there's adding multiple species at a time actually helps a lot with this problem. And then I'm going to talk a bit about the surface algorithm. There's another algorithm I'm developing right now that actually so far works a lot better than the surface algorithm. It has a lot less side effects. If you run into this problem and you're interested in that, email me and I can probably set you up with it. So adding multiple species at a time alleviates this problem because it enables RMG to add all of the important branches at once potentially. So say if you're adding 5 species at a time, you can have the case where you add both C and D at the same time, if they're relatively close in flux and your interrupt tolerance is high enough. If the flux to C and the flux to D are similar, they can reach the same rate in this initial step. However, you can also note that that doesn't protect you in the case where, for some reason, C or D is already in the model before you even go through here, and it doesn't. It also doesn't guarantee you could potentially be adding other stuff at the same time. So maybe you added C because it was the 5th species, and you were only taking 5 species. But I highly recommend adding multiple species at a time for this reason. Doing this tends to increase your model size at constant tolerance, so you may need to increase your tolerance a little bit when you do this. Usually you want to set the maximum number of objects you take. I usually set it to around 5, but you shouldn't set it to like 50, and you probably shouldn't set it much bigger than 10. But anything less than 10 is probably okay. You need to set the interrupt tolerance higher because otherwise it'll only add the first stuff it picks up. And if you're not pruning, you want to tell it to terminate so it doesn't continue the simulation. So once it gets the max number of objects, it'll just stop and be done. So now we're going to talk about the dynamics criterion. So I'm going to go through this. This looks really complicated. I'm going to go through it a little bit fast, primarily because it works effectively, but it also has a lot of side effects for your model. So the idea of the dynamics criterion was to identify the key pathways by concentration change rather than flux. Basically, in this case, instead of identifying how important D is based on the flux to D, we identify how much concentration change it will induce in B. And so we look at some kind of node of some species in a giant reaction network that has some production rate as a function of time and some loss rate as a function of time, and is this pseudo first order with respect to itself. And if we assume that it's relative, that the steady state's approached quickly, not even that it's at steady state, but that it's approaching steady state, and that it's in the vicinity of steady state to a scaling approximation, and the production rate is decoupled from its own concentration, we can get some concentration scale by the ratio of the production rate and the pseudo first order loss coefficient. And we sum across the ratio with the actual scale across this level, and we check whether it's larger than a tolerance. Don't worry too much on the details of all of that.
We have a question from the webcast, actually a bit earlier, but so this person is wondering, how do they know if they have any of those problems in their mechanism? So that's an excellent question. So in general, if you're dealing with low temperature kinetics with oxygenated kinetics, it's quite common that you will have these chain branching cycles can be very, very important because these happen and they strongly influence the radical concentration. I'm not sure if and in theory there's other stuff that can happen at low temperature that can matter. At higher temperatures this usually isn't a problem because everything in general is just breaking down to small species. So this isn't usually a problem. At low temperatures, these sort of cycles can happen. And in general, the best way to recognize that you're missing them is to know what chemistry to expect for your system. But the general takeaway from this is that we get this sort of some expression that's a representation of how much a reaction will affect the steady state concentration of this species over the current approximate steady state concentration. How much it will change this value when we add this reaction to the loss of the production. And also, other thing is that unlike the rest of RMG, this adds reactions instead of species, which changes the dynamics a little bit. So there's a little problem with this, and it's a thorny problem. And the thorny problem with this is that if we're looking at how a reaction affects the concentration of a species in the model, well, the nice thing about Flux is that it has a universal scale. We can look at how big this flux is relative to the overall flux of the system. But with concentration, every species has a concentration. So if we were to just let run in this way and let this do its own thing, what it would do is it would essentially add everything, because it would say, oh, this species is important because it's part of a reaction that affects the concentration of this species. Then it'll add that species, and then it'll look at that minor species that you didn't really care about that much. It wasn't really that important. It was just part of that reaction. And it'll look at that one and say, oh, well, this one needs this to get its concentration correct. And so what was originally not so complicated turned into a complicated, it's a functional mess, but it's a bit of a mess, to be honest. The surface algorithm, which is essentially we define some thing that's part of the core, but it isn't, we don't think it's important. We included it in the core because there were reactions that the core needed that were related to these species, but we didn't think that they had enough flux to be important enough to pull in their own species. And so this creates a bunch of different tolerances. If you want to use this, the details are going to be available in the RMG cookbook, how to set all the parameters. But essentially the idea is that we have essentially this is the important thing to look at, which is that instead of ordinarily adding stuff just like we do with everything else, when we add something with the dynamics criterion, we just add it to this thing. And the stuff in this thing, we don't let the flux criterion pull stuff in related to the flux criterion for those species. We don't let the dynamics criterion pull in stuff that depends on the concentration of the species that we put here that we don't think are important. We also have a few criteria for moving stuff around, but don't worry about this stuff. Essentially, the idea is just that we separated species that we thought were important in the core and species that we added just in order to get reactions in the core that get the species in the core right. So this, there are some sacrifices to this. It does add a lot of species that aren't actually that important to the model, as well as the ones that you need. But it works quite well. So in this case, originally, before using this, they got like this much, this stuff. But with the dynamics criterion, Yawei Che I think she was in the West, working with the West group, was able to add all of these chain branching processes and added all the O2 additions that produce all of these reactions that produce extra OHs. So now we're going to run a little example, do a little practice for the minimal multi-surface example, which is essentially it adds one multi-species at a time and uses the surface algorithm. this case, I've set the the core tolerance and the interrupt tolerance really high, just to show the functionality. But in reality, you don't want the surface algorithm driving your model selection process. It's sort of more of a secondary thing that kind of picks up stuff every once in a while. So the parameters here aren't really realistic ones. The cookbook will tell you what the right parameters are if you want to use this. But this is just a demonstration case. And so I've basically, I haven't entirely turned off the primary flux criterion, but it'll do a little bit of stuff in the own. But a lot of it's off. We have one tolerance. We have two tolerance for moving reactions and species from the unimportant section of the core to the important section of the core. And then we have one tolerance for moving edge stuff that's in the reactions in the edge to the surface, to the unimportant species in the core here. Or no. So it's all good. I'm just demonstrating what's in the file. Going through that. So, in general, what you can sort of see here is that we have some stuff going over the middle entering the core, but we ordinarily with the flux criterion here, but we also now have this reaction itself entering the core, which puts all of the species involved in the reaction into the core. And here we have a bit more of this stuff going on. And as this stuff in the surface moves into the core, we get some of these species start to become disconnected from the surface, and we remove them from the surface. Because they aren't part of any reaction on the surface, because we've moved the surface reactions to the core. Any questions on the surface algorithm? And in general, pickup algorithms, dealing with pickup problems? So to just sort of summarize, I would say that adding multiple species at a time is a really nice, it's an easy way that you can do this that provides some mitigation to this problem with very little sacrifice. The surface algorithm provides a more robust way, but there's some significant sacrifices that you make once you start using it. We're currently testing a new algorithm that works, so far it's working a whole heck of a lot better than the surface algorithm, and it doesn't have any of the side effects. So if you're trying to do this, if you really think there's a pathway you're missing and you're trying to do this, contact me, and I'm happy to let you test that out.
So, in summary, this whole lecture, so RMG runs in two primary regimes: React limited for small models or large molecules, and simulation limited for large models, small molecules. The transition is incredibly system dependent. There's some that it would be entirely impractical to ever reach the simulation limit. There's some that are almost instantly in the simulation limit. If you're running into memory issues, use a pruning algorithm. Try Flux first, and then if Flux isn't working for you for some reason, you can use the thermo-based one. Pickup problems are very rare, but they can happen. And taking multiple species at a time helps with pickup problems. And if you're having trouble picking up chain branching reactions, you can try the surface algorithm, or if that isn't working well, contact me. I'm the primary developer working on this problem. So, yeah. Thanks for listening.